Well, welcome back to the online study of preparing for PPA certification. We're now on Exposures and Meters, Section C. Section C says, verify proper exposure. Now there's 4 items on this section on the exam, and so let's get right into the study and see what we have to take away from it here. The first item is understanding the use of an 18% gray card. Now we're in luck. If you've watched the earlier videos, we've already talked about it, so this will be something of a quick review. If you'll notice here, we've got our white card, our gray card, and a black card. Remember, the meter in your camera is a reflective meter. It measures light reflecting from any given scene. As a matter of fact, it measures light from everything reflecting in a given scene. So when it sees bright skies, green grass, white clouds, black cars, whatever it sees, it's averaging everything within that scene. And so what is the average of everything in that scene? Well, who knows? But we do know the average of black and white. And that average is middle gray, or what we call 18% gray. So when you have an 18% gray card, this is what the camera meter is trying to present to you. The exposure averaged to 18% gray. So by taking the measurement of the amount of light in a scene that is reflecting off of that gray card, then you have the proper exposure. In other words, you simply put that gray card in the very same light where your subject is located. You focus the lens so that it is only seeing the gray card, and you look through the camera and you try to center that meter. You want it to move right to the center by adjusting combinations of f-stops, shutter speeds, maybe even ISO. But once it's in the center, now you know the proper exposure. You can look at how you've set your camera. If you're in an automatic setting, then go ahead and set your camera to manual mode using the very same settings that you got as you were reading it off the gray card, and you will have a proper exposure. You will have the very same exposure that you would have if you had used a handheld meter. Because remember, a handheld meter is an incident meter, and it measures light falling on the subject rather than the light reflecting from the subject. Section 2 says, knowledge of how to read and interpret a histogram. Now, histograms are simply graphic representations of the tonal values within the scene using a scale of 0 to 255. That gives us a full scale of 256 possible tonal values. Remember, 0 counts as a tonal value. When you look at a histogram, it represents an approximate 5-stop range. The blacks appear on the left side of the graph, the whites appear on the right side of the graph, and the gray tones fall near the center of the graph. Again, remember, histograms represent a numerical value of or tonal value of the pixels within that image. So if we take a look at this image of a black card, you'll notice that the histogram is stacked far to the left near the 0. That's because 0 represents black, 255 represents white, and since there's no other tonal values in this image of the black card besides black, then we would anticipate that the histogram should be properly stacked to the left side. In this histogram of the gray card that I photographed, we would anticipate that the tonal values should fall in the middle of the graph because we photographed an 18% gray card, or middle gray. So the histogram bears that out by falling right in the center of the histogram. Finally, in the image of the white card, I would anticipate that all of the pixel values would be on the far right hand side of the graph near the 255. And sure enough, the histogram bears that out. All of the pixels that are represented are shown in this graph on the far right hand side. Now, I've seen a lot of photographers use histograms much to their detriment. For example, let's say they're photographing out on the beach, a beautiful clear sky, beautiful blue water, white sandy beaches. They take a photograph and look at their histogram and say, oh my gosh, it looks like the histogram is way too far to the right. And what they'll do is they'll make an exposure adjustment to try to move the histogram back towards the center. Well, what did we just do in that case? What we just did is virtually underexpose that image, because we've taken all of those high values of the sky and the sands and the water and all the reflections coming off the water, and we've moved them to the center to turn them towards 18% gray, when in fact they should have been left alone. Probably the image would have been much better off just leaving it as it was. So part of your job as a photographer is to be able to interpret the histograms. Now for the CPP exam, I think what we'll find are questions that generally refer to the histogram itself. You want to know that it has a 5-stop range. You want to know that it ranges from 0 to 255, and that 0 represents black, 255 represents white, and middle gray is in the middle. You would also want to recognize that high values such as white will be near the right side of the graph, and the darker values such as black would appear towards the left side of the graph. While not on the test specifications, let's talk for a moment about the zone system. The zone system is a numerical representation of the values between black and white that are based on a 10-point scale. With the zone system, 1 represents black, 10 represents white, and 5 represents middle. We're now on section 3, which is knowledge of exposure compensation, including bellows factor and filter factors. If you'll remember, in an earlier study we talked about the use of bellows between the lens and the camera in order to create close-up or macro images. As you move the principal plane further away from the focal plane, then you also experience light fall off. So it's important to know how to calculate how much additional exposure would be needed when you're using bellows or extension tubes. Now when you first look at this formula, it's a little bit daunting. Bellows factor equals bellows extension squared divided by focal length of the lens squared. Alright, so let's look at the numbers, but don't get rattled here, because I'm going to show you an easy way to calculate bellows factor. In this example, I'm going to be using a bellows extension of 100 millimeters. That means that I'm moving the lens approximately 100 millimeters further away from the focal plane. So again, 100 millimeters bellows extension and using a 50 millimeter lens. So if we plug those numbers into the formula, we get 100 millimeters squared divided by 50 millimeters squared, which turns out to be 10,000 divided by 2,500, which equals 4. So we have a bellows factor of 4. That 4 means that we're losing 4 times the amount of light, and we're going to have to increase the exposure by 4 times. But now think about this, because it's really important. How many stops is 4 times the amount of light? Well, it's 2 stops. Remember, each stop represents either doubling the amount of light or half the amount of light. So if I take my exposure and I open up 1 stop, I'm letting in twice as much light. If I open up 1 more stop, now I'm letting in 4 times the amount of light. If we went 1 more stop, that would be 8 times the amount of light. If we go 1 more, that's 16 times the amount of light. So every time we move 1 stop, we're doubling the amount of light or cutting it in half. So in this case, a bellows factor of 4 represents 2 stops. Since we're talking about 2 stops, we have 3 choices. We can either open up the lens by 2 stops, or we can slow the shutter speed down by 2 stops, or we can increase the ISO by 2 stops. Okay, so here's another simple way of calculating bellows factor without having to do a lot of math. Let's use the example once again of having a bellows extension of 100 millimeters and using a 50 millimeter lens. We're going to take that 100 and sort of think of that more like an f-stop. Let's say f10.0. The next step is just to round it to the closest f-stop. So f10.0 easily rounds up to f11. Now we're going to take the 50 millimeter lens and we're going to round that up to an f-stop. So 5.0, let's make that 5.6. So when you do that rounding up, you wind up with f11 and f5.6. What's the difference between f11 and 5.6? 2 stops. Using the bellows factor formula, we're actually counting the difference in the amount of light. Using my trick little setup here, we're counting how many stops that's different. And that may be an easier way for you to calculate bellows factor. Now we're going to talk about filter factors. You know, when you put a filter on the lens, it could block some of the light or block some of the amount of light that reaches the sensor. Now the skylight filter and the haze filter that we talked about earlier, they're basically clear filters, so there would not be any exposure compensation necessary. But some of our darker filters like the 80A and the 80B that we talked about and the polarizer that we talked about, they're going to absorb some of the light and require us to create at least a larger lens opening or a slower shutter speed or an increased ISO in order to compensate for the light that's absorbed by the filter. So the way a filter communicates that information to you is by something called a filter factor. You might see a filter that has a filter factor of, let's say, 2x or 4x, maybe even 8x. It just depends on the filter that you're using. But what you want to remember is that filter factor represents how much light is being absorbed, not how many stops that you should use. So take a look at this example. Remember, twice the amount of light represents 1 stop. So when you see a filter factor of 2x, that means that you've got to open up the lens or slow down the shutter or increase the ISO by 1 stop, because you've got to let twice the amount of light reach the sensor. When you have a filter factor of 4x, that means that we need to increase the amount of light reaching the sensor by 4 times. 4 times the amount of light is 2 stops. So we again either have to open up the lens or slow down the shutter or increase the ISO by 2 stops when you have a filter factor of 4. Finally, a 16x filter factor represents 16 times the amount of light. Well, 16 times the amount of light is 4 stops. Remember, if you open up from one lens opening to the next larger, that's twice as much. If you go open up one more stop, that's 4 times as much. If you open up once again, that's 8 times as much. If you open up one more time, that's 16 times the amount of light. 4 stops. So again, you have the choice of either opening up the lens or slowing down the shutter or increasing the ISO by 4 stops. Well, that does it for Section C. I hope you found this information helpful. Go back and review it if you have any questions. Review your study guide, and we'll see you on the next section of the test specifications, which is lighting.